Eclipsing?
Yep.
We just started. But I want to start record. Oh, and it's recording.
Yep, it records automatically. It should record automatically.
Awesome. So we start, we've already started receiving participants. Welcome everyone. If you would like to introduce yourselves, please do so on the chat. We have 10 more minutes to go before we get started.
Make sure the phone is muted.
Yeah.
I didn't know Maryland was the rising sun. Arizona, Hawaii, Pakistan, Estonia, Missouri, Italy, Greece.
Hello, Greece. Kalispera.
Scotland, South Africa, Spain, UK, Mexico, San Diego, Canada. I assume that's California. Oh, Normal. I've heard of Normal, Illinois.
Oh, that's wonderful. I should find a really cool soundtrack to play while we're waiting for everyone to join. What do you guys think we should do? Like The Planets by Holst. Gary, you are muted. Gary, you are muted.
I was thinking one of those suspenseful soundtracks from game shows, like, is it Jeopardy that has one? But yeah, Holt's The Planets would be very good. Yeah.
Yeah, oh, really cool. Ooh, we have New Zealand. Welcome. Oh my goodness, what time is it in New Zealand right now?
Late. I believe
early.
16 hours ahead. So.
Well, early.
Yeah.
Wow. Early, 6 a.m. Good morning. Cool. Let's see. Oh, wow. 11 o'clock at night in Pakistan. Good evening, Pakistan. We have about 10 more minutes before we start. Hello, South Africa.
Multiple people from South Africa.
It's really cool. Good morning, Canada. Hello, New Jersey. All right. It's wonderful to see where everybody's coming from. We're, you know, science, astronomy has no borders, and this is a demonstration of it. Wyoming. No, this is Wisconsin. Oh, my glasses. Hello, Spain.
Turkey, Brazil.
Hello, Turkey. Or Belgium.
Pronounced Schenectady. Wow. Never actually known anyone from Schenectady, but I've heard of it before.
Now you do. How do you pronounce it again?
Schenectady. Or
Right.
that's reasonably close anyway.
Thank you.
Florida, Argentina, India.
Hello, Iowa. Finland.
Haven't.
Cool.
Cool.
Very nice. England, Romania. Good to see you guys. Alaska, good morning.
Yeah, I'm not going to try that one.
Yeah. Cool. Hi, Pierre. All right, 5 more minutes to start, and we have almost 100 attendees so far. It's wonderful to see you all.
Mexico City again, South America. Finland. Texas, the Netherlands. Remember that if you want everyone to see it, you have to address it to all panelists and attendees.
Wonderful. We have people coming from all over the world. It's so wonderful to see you all. We're going to get started in 5 minutes. So we're going to allow everyone to log in and settled. No more fires in Tucson. It's good to hear that. Slovakia, Paris, welcome. Italy, North Carolina, New York State. Cool. India, New York. Venezuela, hola. Cool. Qatar, Philippines. Wisconsin, France, everywhere. Very nice, very nice. So while we're all coming in, oh, we're at 160 plus participants at this point. I think I should get started to be respectful of everyone's time. Hi, everyone, and welcome to day 2 of the AVSO Observing Section webinar. My name is Stella Kafka, and I am the Executive Director of the American Association of Variable Star Observers. And today, our special treat for you has to do with eclipsing binaries. We're going to start our science part of the webinar with the fundamentals of stellar astrophysics. I'm joined here with Jerry Samolik, Gary Billings, and Bert Pablo, representatives of the observing section, eclipsing binary observing section. And before I turn back to them, I just want to remind you that we have a chat that you can actually find at the bottom of your screen if you want to send a message to us, to any of the panelists. But if you want to ask a question, there is a Q&A button here where you can actually type your question to the to different panelists, to different presenters. We will start with presentations, and then at the very end, we're going to address as many questions as possible. Also, if you have any technical issues or sound issues, please take a look at this little button here at the bottom of your screen and set your audio settings. There's nothing we can do about your audio, but you can fix it if necessary. So with that, I am going to stop sharing my screen and pass it to Jerry Samolik, who is going to get us started. Jerry.
All right. Sure. Let's start you off with a little movie here. Watch the star that's in the circle and compare it to this star and this star. It doesn't seem to be running. There it goes. That's about 4 hours worth of images condensed down to 10 seconds or so. It's a rather deep eclipse, goes from about 10.5 magnitude, fainter than 13th. Let's see, now I'm going to switch to this one. This is the light curve that was generated from those images. Yeah, nice smooth light curve. So what's going on here is a basic eclipse of one star passing in front of another one. Eclipsing binaries are stars that tend to be inclination of the orbit close to 90 degrees with respect to the plane of the sky.
Jerry, we cannot see your screen.
You cannot see my screen.
No, could you please?
We're seeing the B-Oval movie. So,
okay, let me do this and let me share again. see it now?
Ah,
Perfect.
yes.
Okay, so here we have a star with a orbital plane almost edge on, doesn't have to be exact, but just close enough that one star passes in front of the other one. And this will produce a light curve. When both stars are visible, we're at maximum. In position 2, we get a primary eclipse, back to maximum, and then we may or may not get a secondary eclipse depending on the ratio of the brightnesses. That is pretty much what an eclipsing binary is doing. Okay, now my slides are not advancing.
Click on your screen.
There we go. There are 3 major categories. The first one will be a detached, where both stars are completely independent of each other. In this upper diagram, this intersection represents the Lagrange point between the 2 stars. And these surfaces are areas which would be of equal gravitational potential around the stars. If a star does expand enough to fill that, what we call a Roche lobe, then it becomes a semi-detached, but as long as the stars are completely contained, we have a detached system. The lower diagram, think of this as the gravity well of the 2 stars, where this right here is the Lagrange point, and both stars are contained within their respective gravity wells. If one star expands beyond that, material is going to spill over to the second star, and the star really can't get much larger until the second star fills up also. So in this case, we can see one star has filled its Roche lobe. If this process continues, we can wind up with a contact binary. And now both stars are essentially connected, almost like a dumbbell rotating in space. I'm going to show a few sample light curves of these various types and give you an idea as to the wide variety of eclipses that can be seen. This is a contact binary where both the primary and secondary eclipses were observed in a single night. These 2 eclipses are about 4 hours apart. I should also point out that this is observed in the TG band, which means it was done with a digital SLR. We are seeing some very good data coming with that type of observing. This is a detached system. So we have a first contact and a fourth contact, but nothing, no flat bottom, which means this is a partial eclipse. This is a rather interesting light curve. This is also a detached system. We have a sharp primary eclipse, and I believe the companion is a bright blue star. I think it's a B type. And as the star comes around, we start seeing a reflection of the B star off of the fainter star, so the system's getting brighter due to the reflection. Then where the secondary occurs, it's actually the B star is eclipsing its own reflection. And then it returns, and then the reflection dies away, and we go through another primary eclipse. This is a total eclipse of a detached system. In this case, the totality lasts about 3 hours. When a star gets to have this long of eclipse, it gets difficult to observe the entire eclipse in a single night, but we have enough data here to generate a time of minimum. Sometimes stars have even longer totalities. In this case, the totality is 6 hours long. And since it's a springtime object, the nights just aren't long enough to observe the entire eclipse. So what I did here was caught one night where I could get the first contact down to the second contact. And then 8 days later, I was able to get the third contact up to the fourth contact. So then I subtracted off one orbital period, which is close to 8 days, to make a composite light curve by combining the 2. This is also a very valid method that can be used for determining time of minimum for longer period stars. This is a much longer period star, Zeta Aurigae. In this case, the totality lasts about 5 weeks. And the partial phases are very short. They only last a couple of days. And I'm showing this one to show some of the differences you get with the different filters. Up here in the infrared, you can barely, I mean, you have to use your imagination to guess that there's an eclipse there. In the red, it's a little more prevalent, the V band. When you get down to the B band, we have a nice half magnitude eclipse. This is an artist's rendering of that system. And I've included a table here with some specifications. You can see spectral types are on opposite ends of the HR diagram. Huge discrepancy in diameter, huge discrepancy in luminosity. So the K star dominates, which is why the star is so red. And when the B star goes into eclipse, most of the light loss is in the blue, and even more in the ultraviolet, but my U filter is just not repeatable enough, so I have never gotten good data with it. Beta Lyrae is a semi-attached system. Also a rather long eclipse. This one is about 13 days for the entire period. This does have continuous mass transfer going on. And if we look at times of minimum taken over about 80 years, we have an O minus C plot. And you can see that the period has been rather steadily increasing through this entire interval due to the change of the mass, changing the angular momentum of the system. This is an extreme case of the semi-detached system where we have a main sequence star and the material is pouring onto a very compact target like a white dwarf, or it could even be a neutron star. In this situation, the falling material gains a tremendous amount of kinetic energy. A lot of really interesting physics goes on here. And you'll hear a lot more about these when we get to our cataclysmic section webinar, because this is really what drives a lot of the cataclysmics. There are a number of these that, in addition to being cataclysmics, also eclipse. And that gives us an opportunity to gather even more information about the stars. In this case, these two eclipses are about a little more than 4.5 hours apart. And you might notice that there's a little asymmetry here towards the top. I'm guessing that this may be the hot spot takes a little longer to come out, so we're seeing a little delay in getting to full brightness. But we've also got some oscillations going on outside of eclipse, and that's just what's going on the accretion disk. We have another class, I call them disk eclipsers. And Epsilon Aurigae is probably the best known. It's a very long period, 27 years. The last eclipse occurred in 2009 to 2011. And this diagram I borrowed from Sky and Telescope shows pretty much the idea of what the model for the system looks like. We had a project within the AVSO to observe the star, and this is one of the light curves that was generated. There really isn't what you'd call a total eclipse, but it does flatten out quite a bit as the disk is sliding across. But portions of the F star are visible throughout the entire eclipse. There are some images taken by the Chara array at Mount Wilson, which was actually able to image the disk crossing the F star. This pretty much validated the disk model. EE Cephei is another disk-type eclipser, and in this case, these different colors denote different years of eclipses. And you'll notice that every eclipse has got a different shape, different depth, different duration, and the best guess is that the disk that's doing the eclipsing is precessing. And so every time the disk comes across the primary star, it's in a different orientation and provides a very different looking eclipse. Our next chance to observe this star will be coming up in about a little over 5 years. Now I'll talk a little bit about the Legacy Observing Program. Our primary goal is to take a select group of stars and watch them for basically a long period of time to see how the orbital periods change. This work was originally started by Joe Ashbrook when he was editor at Sky and Telescope. He started running articles back in the 1960s promoting observations of eclipsing stars and publishing predictions as well as times of minimum. Then Margaret Hamill, who was our director at the time, was encouraged to start an eclipsing binary committee, and originally David Williams chaired that committee starting in 1965. Marv Baldwin took over that committee and he chaired it for almost 40 years. And during that time, we were observing more and more stars, and over the time, the legacy program grew to about 200. Most of these stars now we've been observing for at least 40 years or more. In 2008, the AVSO reorganized into the sections that we have today, and Gary Billings and myself became the chairs of that section. On the section website, you will find an ephemeris. Now, this ephemeris is pretty much targeted for North America. Right now, I don't have anything for other parts of the world, unfortunately. Across the top, we have the names of the variables, a magnitude range, which is somewhat approximate. It's whatever was in the GCVS at the time. There is a approximate duration. Now, this is targeted more towards visual observers, and a CCD observer can usually get by with less time. This would be in hours. But do pay attention to totality. This is the V342 I mentioned earlier. It's a 3-hour total eclipse, so if you only watch it for 2 hours, you'll be very disappointed. In this format, we would look at tonight being the 11th, 12th. And if I read across, you'll notice that you have a star like OO Aquili that observes every night, or eclipses every night, and XZ Aquili that you only have maybe 2 opportunities all month. So if I'm planning my observing session, I'm going to go after the star that hardly has any predictions listed, because that's probably a much more valuable target. This is just one page. This goes on for a number of pages. After we observe the eclipse, the next step is to define a time of minimum, or I think of it as time of mid-eclipse. And this is a screen from the Parenzo program. There are a variety of programs out there that all do a pretty good job of determining time of mid-eclipse. And that leads to publications in the journal AVSO. Here we have the name of the star, the time of minimum, and the observer, and then uncertainty. Pretty much every issue is going to have one of these tables. We've been getting quite a bit of observations over the last decade or two. This is another O-C diagram. This is for the same star I started with, Biova Peculum. And on these diagrams, anytime you see an increase in the slope, that means the period of the star became longer, and a decrease in the slope means the period got shorter. And what's interesting about this particular star is you'll notice a segment that's a straight line, which indicates pretty much of a constant period. Another straight line, another straight line, another straight line, and maybe one here. So there are some discrete events going on that are causing this period to change with some years of stability in between. This is the kind of thing that we're really trying to do with our legacy program, is follow stars for a long time and see what they're doing. This was a case of the old visual data had a lot of scatter, but it really was kind of inconclusive. I originally plotted this diagram to the old period that was in a GCVS of 1.9 days. And the first CCD time of minimum came in right about here, and so I thought that would be the period. But then the next few were all quite a bit earlier. And this got me wondering whether there was some error in this, which would, by the way, that's my observation. But then we started getting more observations with O-Cs that matched the first one. And after looking at the table for a while, I realized that these were all even cycle numbers, these were all odd cycle numbers. So we realized that the period of the star is actually double what we thought it was, so 3.8 days. And we're seeing a primary and a secondary eclipse. And star has got a slightly elliptical orbit causing this offset. And now if we look back at the visual data, we can see that there is primaries and secondaries somewhat separated. So the visual data wasn't that bad. Here is a primary and secondary eclipse shot with the same telescope, same camera, same filter, just a few days apart. So we can see there is a slight difference in the two eclipses. This is another case of a star with an elliptical orbit. In this case, the primary eclipse in blue lasts about 4 hours, but the secondary eclipse lasts 9 hours. And this again is caused by an elliptical orbit, but in this case, the primary eclipse happens at the peristron when the two stars are close together, and the secondary happens when they're farthest apart. And because of the Kepler's laws, everything's moving a whole lot slower, the eclipse lasts longer. This is the O-C plot showing the primary and secondaries for RU-MON. And this is a, what I think of as an extremely long-term project, because the estimated period for this rotation of the epsides is estimated at about 370 years. So it's going to take a long time for us to observe one full cycle. Algol was the first, first eclipser and probably the first variable ever discovered. And we're still doing it with the CCD today. And I'm going to go to an O-C plot for that. This is taken from the Brno group, the O-C gateway. So this has got a lot more than AVSO data in it. But over the past century, there have been quite a few fluctuations in the period. And recently a paper was published analyzing this O-C, which introduces two new components to the system. We knew that there were 3 stars in the system, but apparently there's also an Algol D and an Algol E that are contributing to causing the apparent changes of period because the star is being moved closer and farther away from us because of the gravitational effect of the other 2 stars. XE Andromeda is another star we've been observing for a long time. And that O-C diagram also shows a lot of very interesting cyclical variations. And that led to a paper by the same author indicating that there are as many as 10 stars in the system with periods as short as 1.5 years and as long as 92 years, causing these cycles. So this is the kind of results that we get from our legacy program of observing stars for a long time. One thing about this type of observing is we don't need to observe these stars very often. 1 or 2 good eclipses a year is probably enough to keep track of it. So you don't have to take one star and observe it over and over again. Observe a star, then move on to another one. But the value is by collecting data over a long period of time. So I'm just going to conclude by a few things about eclipsing stars. They're definitely fun to observe, and they're very interesting to study. And I haven't touched on the last one very much, but they are very unique laboratories for astrophysics because we get to see the interaction between 2 stellar masses, and we can learn a lot about the stars from that interaction. And that pretty much concludes my presentation.
Wonderful. Thank you very much, Jerry. And from there, we're going to segue to Gary Billings. We already have some questions on what O-C diagrams are. So this is a very natural transition to learn all about O-C. So Gary, all yours. You unmute yourself.
I always forget that. First of all, a little show-off shot. Here was Comet Neo-Y's in the morning sky about 2 nights ago next to my observatory. Okay, on to the topic of the day. First of all, I see we have over 200 participants from around the world, which is rather daunting. And some of you know more about this topic than I do, so I hope I don't blow it too badly. Okay. Okay, hopefully you can now see my PowerPoint screen, and if you can't, somebody please tell me. So I chose this rather strange title because eclipsing binary stars are just so darn interesting. They're fun to think about, learn about, so they're kind of brain candy. And in the context of eclipsing binaries, there are so many things you can do. You can make observations, and not that making observations is trivial, it's a scientific exercise and we all take it seriously, but you can just make those observations, or you can go on to track the behavior of those stars. You can, it's very possible to discover things that no one else has discovered yet about stars that have been in the database for a long time, or new stars that have recently been discovered to be eclipsing binaries, recently discovered in the many all-sky surveys that are going on these days. Or you can not be an observer at all, and you can analyze the accumulated observations that are so readily available by way of the internet these days. So this talk is going to be a bit of an infomercial. Obviously, I have to skip a lot. Some individual slides could easily be a whole workshop. So the batteries are not included. You have to bring some of your own stuff to the table. Definitely some assemblies required, but you can also treat it buffet style and just take the bits you want and not worry about the rest. So what is it about eclipsing binaries we're trying to observe? What observations do we make to get that information? What stars do we observe? There's a lot of stars in the sky. How do we choose them? When do we want to point our telescope at them? And I'll also talk about the types of analyses you can do, and that it's all in the context of the kind of stuff that I like to do. Okay, why are they so important? As Jerry mentioned, Algol, which is a detached eclipsing binary, was probably the first known periodic variable star. If you go to the Wikipedia page, they give some references suggesting about 3,200 years ago, people in Egypt knew that Algol varied periodically. And as Stella highlighted to us the other day, exoplanets are now discovered using essentially the same methods as EB observing. And as Russell said in 1948, he said that eclipsing binaries are the royal road to stellar astrophysics. And that's because when you analyze an EB light curve and you combine it with radial velocity measurements from spectra, that's the only way you can actually measure the mass of a star. I think of it as you've got the second star is like a part of your instrumentation, and by observing its orbit, it's responding to the gravitational field of the first star, and that's how you're measuring the mass of those stars. And finally, they're just fun to observe. You can see action in one night for many of them with an eclipse, and longer term, those eclipses don't always follow a steady beat. The period between eclipses varies, and that's detectable in just a couple of years. So that's quite a lot of fun. Okay, what observations? AVSO is mostly about photometry, whether it's visual or photoelectric or CCD. But for eclipsing binaries, to first order, the light curve is identical in every cycle. And I say to first order because when that's not always true, and when it's not, it's very interesting, but we're going to skip all of that in this talk. So the main goal then is not the photometry itself most of the time. It's to get a light curve through an eclipse, and then you use a piece of software like Jerry was mentioning to measure the time of the center of that eclipse. And when you do that for many eclipses, it's telling you something about the nature of those orbits. And when the interval between those times of eclipses is not completely steady, it's telling you how those orbits are changing. So the most useful observing method for eclipsing binaries is to do time series photometry. And personally, I generally just do one star at night. So I'm doing a time series through the eclipse of a star, and then I determine the time of minimum of that light curve. So which stars to observe? Well, there's two approaches here. One is to continue legacy observations. You know, there are stars, and these are what Jerry was showing you, many of these. There's stars for which we have 50 to 100 years of observations. Well, there's only one way to get 50 years worth of data, and that's to look backward in time. So we want to continue those into the future. Another approach is to observe stars that have almost no observational history. And that's what I like to do. These are stars that have been, many of them have been discovered in recent years by the many all-sky surveys. And those all-sky surveys pump their data into processing pipelines, which do a remarkable job of characterizing the data, sometimes automatically finding periods and classifying them as one type of variable or another. But an intense time series, the type that we make as amateur observers through individual eclipses, will yield a better view of that eclipse and a more precise time of that eclipse. So a few nights of amateur observations can reveal things that those surveys did not. So I often draw my stars to observe from things that have been recently discovered in surveys. Okay. You don't need deep mathematical prerequisites here. A lot of what I'm going to show, especially the stuff about O minus C diagrams, is based on the equation of a straight line that we learned in grade 10 or something. It just says that a line on a graph has an intercept and a slope. And so that's the one mathematical equation you need. You need to understand Julian dates, where we just treat date as a day counter that started at 0 back in 4000 and something BC, and it just increments every day. And the reason we use that is just a lot easier than calendars with different numbers of days in the month and all of that kind of stuff. And it's really helpful if you're comfortable with a spreadsheet. But that's the extent of it for understanding O minus C diagrams, which you've already seen in Jerry's talk are a pretty big topic in eclipsing binaries. Okay, so back to that y equals mx plus b. Well, in fact, we write it a different way. We just change the symbols and rearrange it. So we say the time of eclipse number E is equal to the time of some eclipse that we're going to call eclipse 0 plus the period of the binary orbit times E, that counter of the eclipses. That's all there is to it. And we write that as an equation that looks a bit daunting because it has long numbers in it, but it's really just a very simple idea. So here's 20 years of my own observations of one star, V571 Lyrae, and I've plotted the time at which an eclipse occurred in heliocentric Julian date versus the cycle number. And it's a extremely linear straight line. So that's kind of validating that y equals mx plus b equation. These eclipses for this short period binary star have essentially constant period, and it's fit very well by a straight line. And I'll come back to that in a few minutes because O minus C diagrams are all about examining tiny, tiny deviations from that straight line. Okay, same thing again, that same equation, and these, in this case, these are the numbers for LS Persei. Again, the heliocentric date, which the decimal points represents fractions of a day. So this is really date plus time if you're thinking in terms of a normal calendar. It's equal to the date of for some time that we called eclipse number 0 plus the period of 2.9 days times the cycle number. So this equation predicts the start time of each cycle, and we normally put that as being the middle of the deepest eclipse. Now, you can actually turn this this equation around, because what if you have a whole bunch of observations taken at random times, over a period of years? Well, it's pretty hard to know what to do with those. So you can turn the equation around and figure out where within the orbital cycle each observation occurred. And it's based on the idea that if you make an observation at 1/4 of the way into the cycle, it's going to be the same as making an observation at 1/4 of the way into the cycle of the next cycle and the next one after that. In other words, you're saying that the cycles are going to repeat. So you could take data points from all these different cycles that occurred in all these different orbits and plot them on one graph representing a single cycle. And so that's how you make a phased light curve. And as an example, here's data from LS Persei. These are observations, actually 20 years of data that I observed from dates before I was born by using the glass plates at the Harvard Plate Collection. And when you plot the magnitude of LS Persei versus, oops, I shouldn't play with my mouse while I'm talking. If you plot the magnitude of LS Persei versus the date and time along the horizontal axis, you can see there's a whole bunch of scatter in the brightness of this star, but it's pretty hard to know what to do with it. However, if you use that little equation for determining the phase and then plot each one of those observations from those 21 years, all as if they occurred within a single cycle, then you get this graph, which shows a nice detached eclipsing binary with quite a deep eclipse. And if the numbers that went into that equation were wrong, either it wouldn't make a nice curve, it would just look like random scatter, or the time of the eclipse would be displaced from 0 phase and you'd have to adjust some of the numbers. But we'll ignore that for the moment. So that's, this is actually an example of data mining, but also how to use that very simple equation to make sense of data that was taken at random times. And LS Persei, of course, is still being observed. The big graph here is from the Assassin survey. This is about 4 years worth of data. And again, these data were taken at essentially random times with respect to the star, but then phased into a single plot. Here they've shown 2 cycles. They've just repeated all the data twice. So you're seeing 2 full cycles of the eclipsing binary. And you can see the light curve. Just for fun, up in the upper right is the light curve made from a different set of plates in the paper where they announced the discovery of that. I think it was Karashkin in 1971. But one thing that when you think about it, Jerry talked about determining the time of an eclipse to get a time of minimum, and that's what we're going to analyze when we're looking for how does the period change. One problem with this type of data is if you look at either that previous slide, all the data within the eclipse, some of those data points came from 20 years apart. So if the period was changing, it's probably degrading the curve a little bit, and just night-to-night errors and so on mean that curve isn't as clean as it would be if it was acquired all in one go. And it's the same is true even with the Assassin data. If you look at the actual data points within one eclipse, they're sparse, irregularly sampled, and they occurred over a period of 4 years. Now, don't get me wrong, Assassin is a great data source for us, but if you then go and home in on observing one eclipse on one night, or in this case, I've got the same eclipse from 2 different nights way back in, November of 2005. And you can see that notwithstanding whatever data problems I had, these are really nice smooth curves. So if you're going to run this into a program that determines the center point of this dip, which is what we call the time of the minimum, it's going to work a lot better on this data than on just the points, say, from the Assassin data set. So this is why, as eclipsing binary observers, we mostly do an intense time series through through a single eclipse on one night, or sometimes we stitch together data from a couple of nights. Okay, I'm just gonna mute myself for 1 second, if I can figure out how to do that. Maybe I'll just step away from the microphone because I need to cough. There we go. I don't normally talk this much to myself when I'm in front of my computer. Okay, Jerry showed a bunch of O-C diagrams, and they are central to the observations of eclipsing binaries and tracking their orbits. Also, note that I gave a talk about this at last November's AVSO meeting, and I believe that talk is available by video, and also I posted it to the Eclipsing Binary Forum at the time, the PowerPoint, and that talk was a tutorial about O-C. So it will cover this in even more detail. But the quick version is, let's say you have some data, and I've made this kind of look like eclipsing binary times. So we have the cycle number, and we use that as simple equation that I showed before to predict when an eclipse was going to occur. And then this column is the actual observed times of the eclipses. Now, real observations always have error, you know, just due to uncertainty in your photometry, maybe changing air mass that wasn't properly accounted for, flat fielding problems, whatever. For purposes of demonstration, I've made the error here about 10,000 times what it normally would be, but it will serve for explanation. So the blue points here are the observed times of the eclipses. This was over a span of about 460 days against the cycle number. Oh, sorry, it was, no, it was more like 1,500 days, so 4 or 5 years. So the blue dots are the actual observed times, and the blue line is the fit. Well, most of us would say that's a pretty good fit. You know, we wouldn't dispute the idea that there's probably, the data is well explained by a linear equation anyway. But when things, in real data, the deviation from the straight line would be a lot less. So then it becomes really fruitful to look at how much each of those blue points fell off of the straight line fit. And so the curve at the bottom, what I've done is I've just plotted against cycle number, but now not the actual data, but the data point minus the prediction. And now we can analyze this for patterns. Now in real life, as I said, our data, those deviations would be vastly smaller. So let's look at a piece of real data. This is that graph of my own data from V571 Lyrae that I've been acquiring for the past 20 years. And the data sure looks like it falls on a straight line. But now let's do what I just did and subtract the prediction from each one of those observations. And this is what we get, a very non-random set of data. And that previous graph, the time span on the vertical axis was, well, it was about 20 years. On this graph, it's plus or minus 15 minutes. And you can see there's a repetitive systematic pattern to the data. In fact, it's a light time effect. This eclipsing binary is actually orbiting a third star in an eccentric orbit. And when I fit that data to the equations that describe that case, I come up with this fit. That's a big topic, and we won't go into that for now. It's a lot more than just solving a linear equation. But on the other hand, with the tools that are readily available today, you can solve remarkably complicated stuff quite easily. Okay, getting back to what is a graph like this telling us? Well, here's a simple eclipsing binary. Let's say you're an observer on Earth and you're in the plane of the screen, but way off the bottom of the screen. So you'd be viewing this system edge on instead of perpendicular to that as we are in this slide. So a very simple eclipsing binary that had a totally regular period with a secondary eclipse halfway between the primary eclipse, it would look like this. We think of it as one star orbiting the other, but really they're orbiting their common center of mass. And here I'm implicitly assuming that those two stars have equal mass, and so their common center of mass is exactly halfway in between. and they're both in circular orbits. You can make the next level of complexity is to imagine those two stars are orbiting the common center of mass, but in eccentric orbits. And this is not an uncommon case. And this system will show eclipses at 2 different times. Here's one case. These are the positions of the stars for one of the eclipses, again, assuming that we're a long ways away off the bottom of the page. And here's the configurations of the star for the other eclipse in the cycle. You can add yet another layer of complexity, and this is what relates to the star, the O-C diagram I just showed, B571 Lyrae, where we're observing eclipses of a close pair of stars, and they are co-orbiting a center of mass with a third body. And as it happens for B571 Lyrae, this star does not eclipse that pair. So this is what the star looks like at one point in time. At a later point in time, we're now talking a year or two for 571 Lyrae, the stars have moved like this. And at another point in time, they kind of change places, but they're, you know, I'm running out of words here. I shouldn't try to put words to every picture, I guess. So those are 3 different snapshots in time of this third body system in an eccentric orbit. And so this, this fitted solid line corresponds to the mathematics of a system like I just showed with those cartoons. Now you can actually add another layer of complexity here, and this would also show up in the O-C diagrams, and that is the axes of those elliptical orbits can rotate with time. This is called apsidal precession. And in this case, I've shown it as just 2 single stars, but either one could be a binary pair, and you could be observing eclipses of that binary pair. So there's levels of this sorts of complexity. And it's not just hypothetical. This slide corresponds to the following O-C diagram. This is a star CW Cephei, and the filled circles represent how much the times of eclipses of the primary eclipse deviate from some straight line that's already been subtracted here. So this is an O-C diagram. And the open circles represent how much the times of the secondary eclipse deviate from that common average straight line. And when you see these 2 things being quasi-sinusoidal and out of phase with each other, then it indicates you've got this apsidal precession of the axes of the orbits rotating with time. So this is real data. Again, it's the type of stuff that we can acquire. This data set spans 1933 to 2016. So, you know, you can see, if you're a dedicated observer, you can see action within your lifetime. Another take on that same data, and this is again, sort of eclipsing binary brain candy showing the neat things that occur. This is a star V1103 Cass that it's 2 stars orbiting in an eccentric orbit, eccentric orbits, and the axis of those orbits is rotating with time, and it has a period of, I think, 375 years or something. And through that 375-year period, the light curve corresponding to one eclipse cycle, or one orbital cycle, the light curve changes. The relative times between the eclipses change, and their widths, the widths of the eclipses change, and their depths can change. So lots of interesting things going on. Although this is 375 years, on the first panel, I show you the case for 1999 and for 2018. And so the separation between the primary and secondary eclipses has changed noticeably, and that's readily observable with the kinds of observations we make. Okay, this indicates I'm doing a bit of a transition here. So I'm going to talk a little bit about the types of observing I do and how I choose to find stars to observe. Because, you know, unlike Jerry's legacy stars, these are stars that don't have a lot of observational history. So I'm going to make all-night time series of these stars to, at a minimum, I hope to refine the elements, you know, the parameters that go into that equation, like the period and the T0. I want to revise the elements so the future predictions will be better. And along the way, I will identify stars that are doing something interesting. So I choose to go after less commonly observed stars. One such list is what I've called the Otero Plus list, and it's available on the EB web pages. It's about 1,000 stars that Sebastian Otero and his colleagues identified using mostly from the NSVS survey, which spanned part of 1999 into part of 2000. And many of those stars haven't been observed since they were identified as eclipsing binaries. So I choose to go after those. I live at 51 degrees north latitude, so I mostly just choose stars in the northern constellations. And my observatory is set up so that I can observe them below the pole if I want to. And I choose to go after longer period stars just because most observers go for shorter period stars. Downside of that is if the prediction is wrong, it might be so wrong that I won't see any variation within one night. But that's okay, I'll go at it on another night. Okay, so my recipe here for planning observations is I go to that list of stars and I use a script to identify stars that are going to be eclipsing tonight. You could also do that in a spreadsheet. If you don't want to use that list of stars, you can search VSX at the AVSO website for eclipsing binaries that don't list a period. Those ones are certainly needing some work. And also there's new surveys releasing large amounts of data, both their raw data, but also new catalogs of stars that they found. And so there's, you know, I think this paper announced tens of thousands of new eclipsing binaries. And I haven't even begun to figure out how I will tackle that. But there's lots of that type of work to do. Then I usually go to some sites that are available on the internet, and I will make a reference list available probably by way of the Eclipsing Binary Forum. I use websites from Krakow or the Czech site with their O-C diagrams to see if those sites show recent observations. If they do, well, maybe I will conclude this star doesn't really need a night of observing, or maybe it says, in fact, this star is probably doing something interesting, and so I will observe it. And I can also use those sites to sanity check tonight's prediction. If I can enter the prediction I have for tonight, and if it just doesn't jive with what those sites show for past data, then I know that I probably need to do some more work. Maybe I need to observe it. Maybe I need to look for more corroborating data, and so on. Just a bit of homework to pare down the list of targets that I might observe. And so I will do an all-night time series and get a light curve like I showed you for LS-per. And then I will find the times of minimum, and I will put them on an O-C diagram and see what that tells me about what the star is doing. So here's a very simple example of that. Here's a star V398 CAM, which only has 2 observations. Had one from around 2000. I think it was probably a point that Sebastian and his colleagues derived from the NSVS data. There was another observation from around 2010. And so I elected to observe it. And I then entered my data point on this website, and it then plotted my data point against the 2 existing data points using the period that that website had from probably that they had determined, but you could enter your own elements here if you wanted to. And what I could learn from this was, well, my data is a little bit off the prediction that they would have made using their data, but not totally incompatible. It's probably saying that the period they are using needs to be revised. When there's an overall straight line, but it's not horizontal on an O-C diagram, it tells you that the period was wrong. So the period needs a little bit of revising, but it's not bad. The eclipse only came in 23 minutes earlier than the prediction. Another case, V407 draw, the same kind of background story. In this case, I made 3 or 4 nights of observations. They're very collinear, which tells me that it's not actively changing its period right now, but when I draw a line through my data points, they don't intersect Sebastian's point. So I need to investigate whether it was within the realm of uncertainty of his data, or maybe there had been a period change in between. That's what I found from this star. Okay, another quick transition here to something completely different. So far, everything we've talked about was just using the times of minima that we got from the light curves. Well, the light curves tell us tremendous things about the stars themselves. And there's various ways that you can tackle converting that light curve graph into knowledge about the stars. One tool that I like is this one. The link is at the bottom of the page. It's a teaching tool from the University of Nebraska at Lincoln. And it's an interactive tool where it will generate a synthetic light curve for a model star. So it'll predict the whole light curve based on some parameters that describe the stars. And what's really cool about this website is that as you drag the sliders, and this is just a picture of the website, it won't work here, but when you're at the live website, you drag the sliders, the light curve changes in real time. And so does the diagram indicating the stars. So this is a really useful tool for exploring concepts. It doesn't have as many independent variables as a fancier modeling code, but it's the only one I know of that's truly real time. So it's quite useful. The next level up is another tool that was built for teaching purposes at a university, and it's known as Binary Maker 3. This one you have to purchase the software, it's $100 US, and install it. But it's very useful. You enter parameters as physical quantities, and you then tell it to render the light curve, and it generates the synthetic photometry for these two stars in their binary orbit and plots the light curve for you. It's a little bit harder to use because if you want to change something, you have to change the numbers and then generate the new light curve. But it allows a more complete description of the physics of the stars. And I've used that, for example, this is a star that I did some work on where the black data points are my actual observations through eclipses, and the black solid line is the synthetic light curve from Binary Maker 3, and the red crosses are residuals, which are plotted on a magnified scale on the right. And you can see it's not a bad fit. Now, I maybe didn't use every number between 0 and 63, but it did take a lot of different models to come up with this model. Because the thing is, we're not just fitting a smooth curve through the data points like you might have done in grade school. These models are generated based on stellar physics to actually predict, okay, if you had stars with these masses, these mass ratios, these temperatures, what would the light curve look like? So the results are meaningful after doing it. Now, and in fact, here's some of the numbers that had to go into making those light curves I just showed. This is pretty much a complete list. It's not easy to come up with these numbers because they're not independent. There's a whole art which I only know the smallest bits about. So I only know enough to be dangerous and to talk about it. I don't know. Anyway, it's a very useful tool. Now, you can then move further up the curve. The tools that professional astronomers use are available. You can get them on the internet, and they are the codes that are used in published papers in the top line journals. The most commonly used one is probably the Wilson-Diviney code. It's a venerable code, and it's written in Fortran, and it's batch oriented. You build a little file of parameters and then run the program against them and so on. But as I say, it's available, and some AVSO members use this code and publish papers using the kind of data that we gather and this code to produce professional level papers. A newer code that's in active development and that Bert will speak about next is called Phoebe, and he tells me that it's soon to have a graphical user interface, kind of like Binary Maker 3 did, but with the same kind of completeness as the Wilson-Divinity code, or in fact, even beyond that. Okay, everybody's probably tired of hearing from me by now, so I will end by saying, with eclipsing binaries, there are so many interesting phenomena to study, and it is accessible to us. And you can observe legacy stars that already have a lot of observational history, or you can observe less observed stars. There's something here for observers, people who just want to data mine, and detective work is rewarded. It's not too hard to find something that doesn't exactly fit what you expected based on the already published work. And so you can take your new data and come up with revisions to the period, for example. To do that and to understand what's going on with these stars, you don't need a degree in astrophysics. If you know the equation of a straight line, which describes the linear ephemeris, which predicts when the eclipses are going to occur, and then understand how you could take your observed data and subtract a fit from it to make an O minus C diagram, that's will carry you a long way. And you can discover all kinds of interesting behavior from these stars, and there's a lot of tools and data sources online to work with. Okay, I think I will stop sharing my PowerPoint. If anybody has survived this out there, I will stop talking now.
Gary, thank you so much. Last but not least, let's hear from Bert Pablo on Phoebe, and from there on we're going to go to answering questions that are in the Q&A tab here. So we would like to encourage everyone, we have more than 220 participants, we would like to encourage everyone to type their questions for our panelists on the Q&A little tab, and from there we're going to address as many as possible after Bert's presentation. Bert?
Yes, I will share my screen in just a second, but Gary, you have to stop sharing for me to do so.
Okay, thank you. Very good.
Okay, everyone. So I'm going to talk a little bit on how you might get from observing eclipsing binaries to modeling them. And that is the subject of Mercedes. I saw your question, and Gary answered it a little bit. I'm going to talk specifically about Phoebe. I'm not going to say a whole lot. I just kind of want to get people a little bit interested. And before I start my journey, I just want to say that someone who actually helped me a lot and probably doesn't know it appears to be in the audience today. That is Eugene Milone, who wrote the book Eclipsing Binary Stars, and that was like a Bible to me for the first 2 to 3 years of grad school. It's what got me started with Phoebe in the first place, and is a large reason to why I'm on the development team as it stands right now. Okay, so a little bit of background. The Phoebe was originally a GUI built on top of Wilson-Divinity. The guy who originally built it, Andre Perja, essentially decided that the Wilson-Divinity code was great to work with. It had a lot of physics, but it was hard to use. There were lots of little parameters that you had to change. Everything was done in Fortran, which, if you ever worked with Fortran, isn't the easiest thing in the world. And so he built a nice GUI on top of it so that you can get somewhere a little bit easier. And then that's the way it stood for a few years. But with the onset of Kepler and some of the bigger space missions, it was quite clear that there just wasn't enough physics to model all light curves effectively, especially when you had these very tiny variations. So Phoebe was essentially rewritten. It was no longer a GUI, and it was essentially just a big modeling physics engine to try to address some of the places where things were originally lacking. So what exactly does it do? Well, it has support for a lot of different things. You can add spots. You can have irradiation of the stars. You can create nice little plots like the one to the side here. This was created entirely in Phoebe. You can do this with one simple step, which is just b.animate. And essentially you can create replicas of binary systems by literally placing two stars into orbit around each other. And the two stars themselves are just made up of triangles. Triangles that form an entire surface. Each surface element, each triangle has a temperature, a luminosity, a log G. So essentially you're just you're basically just creating a binary system, putting it into space, and seeing what happens. From that, you can get out radial velocity curves, you can get out light curves, you can get out orbits, the middle plot right there. And there's a lot of other things that are built in or that will be done at some point, but that I'm not going to talk about because the functionality just isn't there yet. It is currently just a Python package. It's pretty easy to install. If you're familiar with Python, there is a pip install to get it to work. But currently, the version that you can download is just that. It's a Python package, and it's not exactly the easiest thing for the novice user to work with. You have to have some familiarity with Python. Then there's a lot of background knowledge that you have to do. So one of the things that we have been working on recently is trying to make it more user-friendly. And when I say we, yes, I am on the development team and I am slightly biased, but I have very little to do with the actual code itself. The main developer is a postdoc named Kyle Conroy. He is amazing at all of this stuff, and most of what you will see is directly a result of his efforts. Oops. So, in the newest version of Phoebe, the paper was submitted a couple of weeks ago at the very end of June. As soon as that paper is accepted, this version will be available. It comes with two things that people have been asking for a long time, but were very difficult to come by. The first one of those is fitting. And when I say fitting, I don't just mean the ability to model the light curve and fit it. I also mean getting a place to start from. If you were to look at a light curve, there's a lot of information held there. But the only way that you're really going to find it or to know what to do is to have looked at a lot of systems and understand what piece of the light curve means what parameter should change. That takes a lot of effort, a lot of intuition, and to make that easier for people, we added something called estimators. These are essentially ways of looking at the light curve and just simply running an algorithm, and it will tell you where the times of minima are, what the eccentricity of the system is, and a variety of other things. Once you have that information out, you can then plug in optimizers. These are just ways of taking those initial guesses and getting to a much more realistic solution. So the red line here is where they started, And after a few iterations, they were able to get to this green line, which is a much improved fit. And finally, after you have your optimizers, the thing that you really want to do with systems like this is to get out errors. That is one of the things that is lacking a lot in binary papers, is that people tend to just ignore what the error on the inclination is or on the masses. And that's problematic, because if you don't have a good error, then how do we know whether or not to trust your solution? So there are a lot of ways to accomplish this. One of these is through samplers. This is this idea that you can run iterations thousands upon thousands of times and basically get a distribution of all of the parameters and how well they fit and how they align together. Now, I'm not going to get into what all of that is or all of the specifics of it, but what I am going to say is that unlike in previous editions, all of this flexibility is now within the Phoebe framework. You can do all of these things without having to write your own code or take models from Phoebe and plug them in somewhere else. This is now a much more cohesive ecosystem. And finally, which I know a lot of people have been looking for a long time, when this release comes out, it will come out with a UI. Now, in this UI, you can add parameters, change parameters, view graphs almost immediately, add data sets. A lot of this stuff is very difficult to do on the command line, and this makes it so much easier. But the coolest thing I think about the UI is that it interacts seamlessly with the command line itself. If there's something that you can't do in the UI, you can pull up a command line window and do it there. Or vice versa, if you're in the command line and it's a pain to enter parameters, you can literally pull up a copy of the GUI, enter your parameters, and then go back. So it's this flexibility, which I think is amazing and which is worth a lot for people to look at. And while I won't say that any of this stuff is easy, it is at least easier. And that's something that we've been striving to get for a long time. So thank you for listening. And at this point, I think I'm done.
Excellent. Thank you, Bert. And if I am allowed to share my screen for a second, share my screen. Here we go. This is the Eclipsing Binaries page, just for those of you who would like to get more information. You have information on Introduction to Eclipsing Binaries. This is the URL, Introduction to Eclipsing Binaries, targets, the target list is there, and all kinds of resources about Eclipsing Binaries. So if you want to learn more, if you want to refresh your memory, and or if you would like to be involved in one of the observing programs, please go here. From there on, this webinar is going to appear on our YouTube channel. Please join us in social media. We're very active there. If you're not a member, consider to become a member of the AVSO. Full member is $85 US a year, and definitely student discount rate. Support us. All this is offered to you for free by our staff and our volunteers. And here's a contact email if you have any questions. And from here, I'm going to transition to our Q&A, starting with a question that actually is addressing something that Jerry discussed, algo. So the question was, what was the time range of change in the O-C plot for algo? We're talking about hours, minutes, seconds, years. Jerry, want to answer that?
Yeah, I'd have to bring up the diagram to get a look at that. Don't have that off the top of my head. Give me a little time to dig it out.
Okay, so while you're checking that, can I move to a question for Gary? How to measure time of minimum and time of maximum of light to calculate O-C?
Okay. What we normally do is we use a program, one of several programs where you input the data series that made up the light curve through the eclipse. Oh, by the way, I noticed somebody said, well, what is a light curve anyway? I guess I should apologize. We should all apologize for not saying that explicitly. A light curve is just a graph of how the light changed with time. The brightness of the star changed with time. So many of these light curves that show a dip, like a valley, that showed how the brightness decreased going into the eclipse. Maybe it was flat at low light level, constant low light level at the bottom of the center of the eclipse, and then it rose back up to the out of eclipse brightness where you're seeing both stars, all the light from both the stars at the same time. That's the light curve, an eclipsing binary light curve that we're mostly working with here. And so we would feed in those same data points of time versus brightness into a program that finds the point of symmetry in that dip. There's various programs. One that I use is called AVE. It's quite an old program available on the internet. Another one is Paranso. And Bob Nelson has one called Minima 25 or something that uses various methods, various algorithms to find the point of symmetry of that shape on your graph. Now, there's a whole bunch of assumptions that are made in these programs. Most commonly, they assume that the graph is symmetric, but that's perhaps going into more detail than you want.
Thank you, Guy. Jerry?
The total amplitude of that O minus C diagram was maybe an hour and a quarter.
Wonderful.
So it was substantial.
Thank you, thank you.
And actually, I'd like to follow up on something Gary just mentioned about using these time of minimum programs. What I've usually find is useful is the program will give you the opportunity to choose a beginning and end point of the data that'll be used in the analysis. And depending on the light curve, I may pick several different intervals and compare the results to see how consistent they are. And if there is any asymmetry in the light curve, this is usually a way to find that.
Wonderful, thank you. A question for both of you, for new observers. The individual asked, I knew I'd rarely observed EBs, but also see that they often don't have many comparison stars. Do you perform differential or all-sky photometry? More specifically, what advice to have for amateurs to attempt to observe EBs with few prior observations that do not have comp stars when using the AVSO observing charts? So for the answer, can we start with Gary?
Okay. I've been doing this for about 20 years, and I mostly choose my own comp stars, which I probably shouldn't. So Jerry could probably give a better AVSO answer in a moment. But I choose stars that fit my field of view, and I use APAS to choose stars that have similar brightness and color. So it's very, it has to fit your telescope, and implicitly there I'm using purely differential photometry. I do it all V filtered, as Jerry, I guess that was before the webinar began, but I use V filters to minimize color variations causing problems, but then it's differential photometry.
Jerry?
I pretty much use the comp stars I find on the variable star plotter. And over the years, I have made requests to our sequence team about stars that we needed more comp stars. And for as far as the legacy stars, they've got a pretty good set of comps for all of them.
And we would like to add that our sequence team is doing an exceptional job providing comp stars when they aren't there. So if there's an object, if there's a star that you would like to observe and it doesn't have any comparisons, please contact us. This is our webpage, our contact email address, and we will actually send your request to the sequence team to provide comparison stars for that. But as Gary mentioned, the APAS All-Sky survey provides appropriate comparison stars, standard stars in all fields. So you will find something in your field of view. So you both talked a little bit about filters. So we have some questions about filters for EB observations. Any advice, any preference? What would you guys advise?
I usually use the V filter for most of my observing. On some of the slower, the multi-day eclipses, I'll usually shoot 4 filters, B, V, R, and I. I do think it's a mistake to shoot unfiltered. I have gotten into trouble where if you have comp stars that are too different in color, you can see things that aren't really there just because of the differential atmospheric absorption of the colors.
Thank you. Gary?
I also just use a V filter. I don't cycle through all 4 filters. In fact, some of my cameras, I just have a single V filter screwed into the camera. And so it's not transformed, but still it should be much more reliable than just shooting unfiltered. But if you were working on a star that was really faint, then you may want to go unfiltered. However, that kind of leads to another philosophical question, which is, if you're pushing things that hard, is this a good target? You know, sometimes maybe it is, but there are lots of stars to suit different magnitude ranges, and you might be better, rather than having to go unfiltered, you might be better to shoot a star that's a bit brighter, and you'll have more resilience against noise and other problems.
Yeah.
Another option when you're shooting a particularly faint star would be to go to an R filter instead of a V filter, because the stars tend to be brighter in red and the chips tend to be more sensitive in red.
Very good point. Which segues us to another question. Are there any top 3 practices for CCD observing at the telescope?
Please repeat that.
Top 3 practices for CCD observing at the telescope. So you have a telescope and CCD camera. How do you even start observing these stars?
Well, one thing I always remind observers to do is to check their computer clock. You cannot take for granted that it's accurate. We're reporting observations of 5 decimal places of a day. So keep that computer clock within 1 second of actual time.
It's a very good point.
Yeah, that's key.
Especially when you're looking for timings, right?
Correct.
Yeah, very nice. Here's another question. Which catalog can I use for getting U and I magnitudes for comparison stars?
I haven't looked at any U at all. There are a number of I magnitudes available on the variable star plotter, but you have to check the right boxes to make sure it's going to give you that information.
Thank you. Bert, this is for you actually. They're asking, where can we find this Phoebe Python package?
If you install, I mean, you can literally just do pip install Phoebe, or you have to do it in Python 3, but you can do that. If you want more information, and you can download it from here as well, you can go to phoebeproject.org. Let me put that. The link will be sent out after the seminar, but I will put it in the chat for anybody who would like to check it out.
Wonderful, thank you. Another question says, do you know of any star systems with a lensing effect from a neutron star eclipsing a main sequence star that is accessible to amateur observers?
I don't. I do know of a few neutron stars in binaries, but I don't know of any that lens. Yeah, I couldn't answer that. I'm sorry.
Okay, all right. Another question that came, there's a, if the star you observe is unidentified, how can you tell the difference between an exoplanet candidate and an eclipsing binary? Is there any chance that you go for an identified eclipsing binary and in the end have an exoplanet transit or vice versa? Mm.
I've just been, I was just partly typing an answer to that question, but maybe it's easier to speak it, and Bert and Jerry may well wish to add something. This is an excellent question because, as I mentioned, the method we use in observing eclipsing binaries is actually the same as the transit method for detecting exoplanets. We're just looking for a drop in the light curve. I think you're unlikely to mistake an eclipsing binary. Let's see, there's a greater chance that an exoplanet candidate was an unrealized eclipsing binary. For example, an eclipsing binary in the background of the star that you were looking at. So you thought you were observing a certain star, but extremely close to that in the sky and far in the background was another eclipsing binary. And so you're observing the combined light from the two of them. And that could make a very small drop in the magnitude that you observed. And so you might think it was an eclipsing binary. And so the Kepler team had to kind of validate their exoplanet candidates against that problem. Now, the other way around, you're unlikely to think it's an eclipsing binary when in fact it's an exoplanet, because exoplanets, the magnitude drop is like less than 0.01, but all the EBs we've been talking about here, the drop in magnitude in the eclipse is at least several tenths. You could, in principle, have just a grazing partial eclipse and get a very low drop in magnitude, but that's not a common case.
I was just going to say there are two cases in which you might have an eclipsing binary mistaken for a planet. And that is one that's very common in tests if you're in a super crowded field. So test pixels are very large. So if you have a bunch of stars, then the amount of light drop is going to be a lot less than the system actually is, because you're including a bunch of extra stars. The other one that I have seen personally and actually experienced is if you have a giant star with a much smaller dwarf star orbiting it, you can get eclipses that are pretty tiny, a couple of %, which would be equivalent to a fairly large planet if it were a regular star. But since it's a giant, which is huge, it actually isn't.
I think another comment about exoplanets is that of course, the planet's much smaller than a star, so you will tend to get a relatively short descending portion, a flat, and then a short ascending portion.
Yeah. And we're going to discuss more exoplanets next Saturday. So for those who are interested, join us next Saturday as well. Here's a question about a specific star. In LS per star light curve, there was another dip in the curve other than a major one, and it was periodic too. How can it be interpreted? LS per.
LS Hercules?
Perseid, PER.
Oh, I'm sorry. I thought I heard Hercules. So I was going to say that's an R11 star.
Yeah.
Oh, so that's a star that I showed several light curves for. And I'm sorry, Stella, could you run the question by me again?
There was the question was that there was a second dip in the light curve other than the major one, and the second dip seemed to be periodic as well. So what is the interpretation of the second dip?
Oh, very good question. And again, it hits on something that I probably should have explained. That's the secondary eclipse. Mostly I was talking about the primary eclipse of LS per, but in fact there is a secondary eclipse. Instead of, the primary eclipse is star A in front of star B, let each of them do half an orbit, and now star B is in front of star A. And in the case of LS per, the primary is very deep and the secondary eclipse is quite shallow. So that's what the questioner was seeing.
Wonderful, thank you. Another question, how can we do phase fold and average light curve in one task only? Is it possible to do with Excel?
Yeah, I do phase plots with Excel all the time. The equations are relatively trivial. In fact, most of the light curves I was showing is generated from Excel.
Wonderful. Thank you. How do you work out the period to calculate the phase when the data is taken at random times?
That's an excellent question, because I kind of just never really talked about that problem. I'm mostly working with stars for which somebody has already made a phase estimate. But if you have a bunch of data, you know, for example, that looked like my LS per data from 1930 to 1951, the data is just scattered all over the map. So you know that something is going on with this star, but you don't even know if it's an eclipsing binary or not. So you're having to search for a phase from scratch. There are period finding algorithms for doing that. And I believe several of them are implemented in VStar. Is that correct?
Yes, I think so.
Yeah, so VStar is a really useful interactive cross-platform software package that's available for free from the AVSO.
It's just a Java, yes, it's a Java software that can be downloaded and used widely. So we have a question here. Can you spend a bit more time discussing filters? Which one to use and when, and where are the specification for each filters? Where do obtain specific types of filters for CCD observations? For the observers in our panel, Jerry, would you like to address that?
I had been buying my filters from Astrodon, but I haven't purchased any for quite a while. I've been seeing a lot of discussion that filters are getting more difficult to come by.
That said, and I agree with that problem, because I'm thinking I might like to buy some additional filters and I don't know who to go to right now. This isn't my main area of expertise. This would really be a question for Arnie. But I think many people are getting pretty good results using like LRGB filters. You could use the G filter, the green filter. It doesn't have the same pass band as a standard V filter, but it would reduce the amount of spurious variation that you would get due to spectral differences or differential absorption. But I'm not the best person to answer that question.
Yeah. So actually, you know something, I would like to encourage individuals who are interested in specific filters and observer modes to come back to the webinar that we have from the observing section for instrument and equipment. This is in September. And also, please use our forums to ask specialized specific questions if you're interested in learning a little bit more about how to get started, what kind of filters and observing equipment you might need for different types of objects that you're interested in. Here's another one. Do we have practical tutorials for data processing at AVSO website or in the courses? And I'm going to answer this question. We do have practical tutorials, and actually we do have choice courses on both VStar and VFOT, which are the pieces of software that the AVSO is providing for its community. So please take a look at our choice course schedule in order to see when the next one is being scheduled, if you're interested in attending one. And of course, we do have manuals, tutorials for those who are interested or prefer to read by themselves instead of attending a course. Here's another question. I haven't heard transformation of filtered observations discussed at all. Is there any need to transform one's data for repeatability of observations by others? Who wants to answer that first? Gary, I'll start with you.
Since I don't transform. Well, I guess partly my excuse for not transforming is this way all my telescope time goes into data points that lie on the eclipse curve in one band. I do see sometimes people publish times of minima for 4 different filters in one night. So they were spinning through all their filters, and so each of their light curves is going to be more sparse. And I observed that their times of minima disagree by sometimes quite a lot more than the uncertainty in each time of minimum. So I don't really know what to make of that. But as I mentioned, I only observe through V. Yes, oh, sorry, let me back up half a sentence. Eclipsing binaries, mostly, as you can tell from our talks, mostly we're talking about the times of minima. So being able to put everybody's actual photometry on one graph isn't as critical as it is in other activities. I'm not saying that proper transformed photometry isn't useful. For example, one thing that we don't do as eclipsing binary observers is we don't monitor very much the actual magnitude of this eclipsing binary pair over time. Mostly we ignore that. And that's probably a missed opportunity. I know of one case where the folks at Harvard College Observatory, when they were doing their DASH project of scanning all their plates and going back and doing photometry over the past century, they found that one well-known eclipsing binary actually had a huge brightness event, a big magnitude fade back in the 1930s that nobody ever noticed because we were only thinking about the times of minima. So that's probably the reason, is mostly we're just taking the light curve. Doesn't matter if there's a 0-point shift and we're getting time of minimum, but if you want to do transformed, go for it. Your data has potentially more uses if you do that.
Jerry?
I was going to pretty much reiterate what Gary said about times of minimum. That's pretty much what I work with. And I do analyze each observer's data independently. And so it's not really an issue. I'm never really combining observers. But I do agree that transformed is the best way to go. It's just more work.
Yeah. We're going to address a philosophical question here. How could discovering these binaries affect our knowledge on Earth or our real lives? To boldly go.
Well, I would say observing binaries affects my life because I really have a lot of fun doing it.
I mean, that's a difficult question to answer. You could take it a lot of different ways, right? I basically focused my life around binary stars. It's what I do. It's what I love. As to other people, there's a lot of different ways that you could think about it. For instance, a lot of the observational techniques, the cameras, all of the stuff that we have now, the technology was driven by astronomical observations. That's what pushed CCDs to get better. That's what pushed cameras to get a lot better. And one of the primary things that people observed for the longest time was eclipsing binaries, because they're one of the easiest variables to both identify and learn from. So.
I'll take a stab at this too. Interesting question, not one I think about every day. But I think there was a clue in that quote I made of Russell, who talked about how eclipsing binaries are so key to understanding stars in general. A key factor in modeling how stars work, how much energy they put out, how they evolve through time, you know, all the way out to billions of years. A key parameter is their mass. That's the thing that determines the color of stars and hence their temperatures and their lifespans. So eclipsing binaries are all part of this huge mix of getting information about stars. And hey, everything about our climate is driven by our star. So I'm not saying that if we stop observing eclipsing binaries today that we're going to have a climate catastrophe, but it's all part of the intellectual milieu that you can't really predict ahead of time what's going to be useful and what's not. And that, and the fact that humans are curious creatures. We first started wandering away from where our species was born hundreds of thousands of years ago, and we've been at it ever since. It's what we do. So that's enough philosophy for me right now.
Jerry?
Well, as I said earlier, that's pretty much just gives me a lot of fun, and we're all amateurs for the most part. We do this for a hobby. We do this because we want to enjoy it.
Awesome, wonderful. Let's go back to techniques here. We have a question. What tools do you use to align the observation sets from different nights or different sources to obtain a smooth phase diagram?
Well, Excel is a very powerful tool. It's very easy to use that, to take my equation for the straight line, that predicts the time of eclipses. You then turn the equation around to give you the phase within an eclipse. So you can take an observation from any Julian date and figure out what its phase would be, and so stick it into a phased light curve. That's very easy to do in Excel. So that's probably the easiest answer for most people.
Anything to add, Jerry?
Pretty much the same answer. I use Excel very heavily.
Very nice. We have a question about radial velocities here, whether amateur equipment can acquire radial velocities for eclipsing binaries.
So I just started to answer this question. The simple answer is yes. I've used radial velocities derived from amateur spectra. The more complicated answer is that it's going to depend strongly on what kinds of stars you're looking at, their brightness, how short the period is, because that will determine how big the shift is. The shorter the period, the more easy it will be to determine radial velocities, because they'll be moving a lot faster. And it will also depend on the resolution of your spectrograph. So yes, but exactly what you can observe will really depend on your setup and what you're trying to accomplish.
Do we have to worry about limb darkening coefficients and filter passbands when modeling an EB system like needed for exoplanets?
Yes, you absolutely do. However, the way that Phoebe handles it is a bit different. So instead of having limb darkening, which is basically this idea that across the disk of the star, the limb is darker because you're seeing through the outer layers, and at the center it's brighter because you're seeing down into the core where it's hotter. So if you take the model and instead of applying a limb darkening law for that, what Phoebe does for its atmospheres is it just says, instead, I'm just going to take the actual luminosity at a grid of points across the surface of the star and interpolate between them, as opposed to just guessing at the limb darkening law. That is the approach that we take, and it's what we use when we can. Unfortunately, not all atmosphere models are available to us for that. So if you're looking at really, really bright stars, or sorry, really, really hot stars or really, really cool stars, you will have to do the limb darkening on your own. But yeah, it's definitely something that you're going to have to consider.
Thank you. Another question, Gary, specifically for you. Is there a way we could see some of your Excel code?
Well, I'm not averse to that, but seriously, it's extremely simple. The equation of the straight line is almost the simplest formula you can implement in Excel. The one that's a bit tricky is to reverse that equation to get phase. And I had that on my slide where you use the mod function to just get the the fraction of the phase. So maybe if you need more information on that, maybe start a question on the AVSO forum and we can pursue it a little further.
Thank you. For DSLR photometry of EBs, is it useful to extract all 3 colors and submitting that data? Jerry?
I really don't have any experience with that. Most of what I'm receiving is the green. I would think that it would be interesting to take a look at all 3 colors and see if the time of minimum is the same for all 3 or if there's any trend one way or the other. I do know of one AVSO member who's been doing 3 color with the CCD, believing that he's seeing differences in the time of minimum based on color.
Gary?
I haven't done any DSLR photometry myself, but I note that with a DSLR photometry, you're getting all 3 colors at the same time. So you're not losing any observing time in one color by shooting in another one. So if you're up to the extra data handling, I would say, why not? The question then becomes interesting if you derive different times of minimum as to whether it's real or due to data problems.
So the one thing that I would add is that more data is always better. The one thing that I don't know about DSLR from the point of view of modeling is that typically speaking, when you model an EB, you have to put in the filter. So Phoebe expects you to have a filter for the data, which is fine as long as you have a passband to put in. You can do that yourself. But I don't know if they are actually like passbands or transmission curves for the DSLR filters or for the colors. If anybody has that information, I would love to have it, and I would put it into Phoebe myself. But as far as I have seen so far, no one has been able to give me that information, which is the one caveat that I will draw if you're really looking to model it.
I just happened to be Googling that topic the other day and did find a bunch of graphs that claimed to be showing you the different passbands for a variety of different DSLRs. Now, I have no idea how reliable they are, but they did show quite a lot of difference.
Thank you. Now, how do you update times of minimums? How do your updated times of minimums get into VSX or other databases that your work is actually useful to future generations?
Well, the papers that we publish in Journal AVSO, I send electronic copies to the BAV, so it's included in the electric connector database. I send a copy to the Brno people for the O-C gateway. So we do try to share information with the other organizations. And then when people are looking for it, our data will be included with everybody else's.
When you talk about eclipsing binaries, are you referring only to extrinsic variables? What about intrinsic? What are the difficulties in determining the period when there is eclipsing and, say, pulsation?
Well, that does add a whole nother caveat.
There we go.
One case that I have observed is VVCPI, which is it's a long period eclipser, but it's also an intrinsic variable. And so analyzing the eclipse can really be a challenge. One thing I tried to do is look at the I band because the eclipse is almost non-existent. And I tried to get a correlation between the variations in the I band and in the B band, and then find a way to subtract out the pulsation so I could look at just the eclipse. But it's not a trivial thing to do.
So one person's noise is another person's signal is a pretty common sort of statement. I actually look specifically at EBs that have pulsations in them, and it does make things harder, but there's a lot more information that you can derive from it. Astroseismology is a big branch of work that's being done, especially in the binary community now. But it does make life more difficult. You'll have to isolate the signals. A lot of times you create a binary model, use that to subtract it off, then look at the pulsations. use a model for those, subtract that off, go back to your binary model, fit, iterate. All of that takes time and effort. Theoretically, in the future, Phoebe will be able to handle pulsations. It's one of the things that that is technically in development. So if your program can do it, then that's great. But yeah, it does require a lot more work.
Wonderful. So we have 10 more minutes until the end of the hour. So I would like to give you guys opportunities for some final thoughts. How do we get started with Eclipsing Binaries? How can we join the AVSO Eclipsing Binary Observing section? What are your thoughts?
I'd like to encourage anybody who is just getting started, never done this before, to start off by observing a few of the legacy stars. Send me a copy of your data and I will compare it to other recent observations and let you know how you're doing. It's one way that we can build confidence in your process, that if you want to go off and do some of the new discoveries and chase something else, you're confident that you are doing the correct process.
Gary?
I fully endorse what Jerry just said. I talked a lot about the exciting stuff that EBs can show you, and you know, when you get beyond all the first order effects and you look at how things deviate from the normal expectation. So that's not a good place to start. You want to be comfortable with normal situations, and then layer on the complexity. You'll probably find it very discouraging if you start out by trying to observe something that has no observing history. Amongst other reasons, it could be there's a reason for it. Maybe it isn't a variable at all, and it's a database error. So start small and work your way up.
And I've actually had cases of people who are getting into exoplanet observing who will try a few eclipsers just, again, to make sure they're doing the right process.
Yeah.
It's easier to go after something with a nice high amplitude before you go after these millimeg events.
Yes, because we skipped over the entire process of how to find things in the sky, how to set up and run a telescope and keep it working, and you know, a whole wealth of observational stuff that a person has to learn. And we kind of assumed that you've already mastered all of that.
But for that, we will have a different discussion towards the end of September. And that actually helps us wrap up this session. Bert, any final thoughts?
No, not really. Just thank you to everyone for attending. If you have any more questions, please feel free to let us know, either on the forums. My email is out there. I specifically love EBs, so I'm happy to talk to anyone about any questions or point you to resources if you would like them.
Wonderful. And with that, I would like to thank Gary Billings, Jerry Samolik, and Bert Pavlov for an intriguing subject matter discussion. We learned a lot about eclipsing binaries, classic, honest to God, fantastic science done on really complicated systems. You think about it, all kinds of knowledge that we can derive out of it. Please come back next Saturday. We're going to be discussing exoplanets. And with that, thank you all for joining us from all over the world. Our best regards. Be safe and talk to you soon. Bye.